all of a sudden, string theory went from being a mathematical curiosity to an actual live candidate for which could potentially be the universe around us. It's a logical possibility that the world around us really is described by string theory. And if we had good enough microscope, we could see the little strings as we looked resolved to smaller and smaller distances.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 136. And this special episode is with Andy Strominger, who is Gwill E. York Professor of Physics and Director of the Center for the Fundamental Laws of Nature at Harvard University. And this episode is special for a few reasons. One, it's the first on the show of many to come that touches on M-theory, which you might not have heard of, and which I think I might even be the only person who says M-theory in the podcast, even though it is the subject of our conversation. And that's because M-theory is generally referred to, as Andy mentions as we talk, it's referred to as string theory by those outside of the profession, though more technically, there are 5 10-dimensional string theories, type 1, type 2A, type 2B, heterotic O, and heterotic E, which combined with an 11-dimensional theory, supergravity, fall under the umbrella of M-theory. And we don't get quite to this level of detail in our discussion, but the second reason that this episode is so special is that Andy is one of the absolutely key figures in string theory / M theory, and he solved some massive outstanding problems like that of Bekenstein-Hawking entropy, which we get into. And a third reason this episode is so cool is that we talk about some of the biggest questions in the universe in physics. So singularities, black holes, the unification of quantum field theory and general relativity. And we start off with Andy's background. Then we get into the quote unquote crisis in physics, which is that aforementioned incommensurability of quantum field theory and general relativity that I just referenced. And then we turn to the basics of string theory, Calabi-Yau manifolds, and the peculiarities, or at least for our intuitions, of extra-dimensional spaces. So 2 caveats. I'm going to go with caveats worth mentioning. First, right at the beginning of the episode, the first thing I say, I get one of the dates of Andy's publications wrong, and then I blame it on Wikipedia. And later on, I checked Wikipedia, and in fact, the entry on his career, and I confess, I do occasionally use Wikipedia to get some background biographical details, these sorts of things, right? The entry doesn't even mention a date at all, so it was just entirely my memory that was wrong. So I egregiously and unacceptably besmirched Wikipedia's reputation. I apologize, and I will do better. And the second thing worth mentioning is that we talk a bit about the Anthropic principle, which we don't actually define, unlike many, but not all of the other things we discuss. So in the interest of doing that, the Anthropic principle is basically the idea that the universe is fine-tuned the way it is. So the particles are such and such, the forces so and so, because if they weren't exactly the way they are, then we would not exist to observe the universe. And in other words, of course, we observe what we observe about the universe because it would be nonsense to suggest that we observe anything else, as that would preclude our existence and hence our ability to observe these things in the first place. All right, long spiel. So reviews, comments, likes, please, all those things, they're great. And then without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Andy. What I'd really like to talk about today is an overview of a field that has been a major part of your work and to which you have in turn made major contributions, and that's string theory. And I'd like to begin with how you got started in the area. So my understanding is that Leonard Susskind here at Stanford and then a couple of other physicists independently arrived at the modeling of nuclear forces with strings around 1970. And then I saw that you got your PhD in 1982. So were you working on early formulations of string theory at that time already, or how and when did it land on your radar? Because I know that you and your colleague Kumrun Vafa had already made a pretty breakthrough contribution by 83.
I think your dates are a little bit off. I think Kumran was a second year. I'm a couple of years older than Kumran. I think he was a second year graduate student then in 83. 85, maybe 84, 85.
Okay.
It was the Columbia Spaces.
That is totally possible.
Yeah. Okay.
I'll just interrupt you off the bat, but I was talking to a historian, Norman Neymark at Stanford a couple of days ago, and I think I got that date from Wikipedia, and I informed him at the beginning of our interview where his parents were from and what his religion was, and I was totally wrong. So Wikipedia.
Okay, this is a small
mistakes.
Yeah. I was in 83. I was when I started to learn string theory. I hadn't done anything in string theory in 83, but yeah. So what was ask me your question.
Sure.
There's so many ways into this subject. How did I get it? Okay. So I think of string theory really as a tool. It's not a question. And it's not the question. Well, there are many different questions that physicists, theoretical and experimental, are interested in. And the one that I became interested in and decided to devote my life's work to trying to understand is the problem of quantum gravity. And that's the problem, a very deep problem. It's there. Quantum mechanics and general relativity aren't consistent without something else and without some kind of framework, or at least on the face of it, they're inconsistent. And we believe that the universe is consistent. We have overwhelming experimental evidence for quantum mechanics, overwhelming experimental evidence for Einstein's general theory of relativity. And so there must be some way that these theories fit together. And that's a problem that we're going to have to solve sooner or later. And I don't mean by that I mean for sure in the next 500 years, we better solve it. Hopefully we solve it in the next 5 years, but it's there. It's not going anywhere. And whether or not it's a smart thing to work on, or whether or not now is the time that we might be able to make progress on this, that is not a question that there's a scientific answer to. All scientists are gamblers. There's a lot of problems that are presented to them, and they have to guess which ones can be solved. If you do which ones can be solved, the game's over. So as a graduate student, I kind of assessed the state of physics, and quantum gravity looked to me like the problem that we could, there was a good chance that we could make some progress on it, in my lifetime, and maybe even solve it, Now, string theory has a very peculiar history. As you just mentioned, Lenny was Susskind, other people, Veneziano, Bersaro, Josh Schwartz, many people were thinking about it, but largely not motivated by quantum gravity at all. And they were trying to solve the theory of the strong interactions. And Lenny in particular had made some important observations about the structure of baryons and mesons and their possible relationship to a string. And that enterprise of trying to use string theory to understand the strong interactions in a very direct way has been good. It hasn't been spectacularly good. It's not the main way that we think about the strong interactions. It could circle back around and be more useful for that than it is. But where surprisingly different problems in physics, it often happens that two problems that you think are different become the same problem, or a mathematical method in one problem is applied to another problem. My favorite example of that is Yang-Mills theory. So Yang and Mills, they were trying to understand the relationship between, this is in the 50s, they were trying to understand the relationship between the proton and the neutron. And they proposed a very beautiful theory called Yang-Mills theory, in which proton and neutrons are two faces of the same object, same fundamental object. And it was a clever idea, turned out to be wrong. However, we now know that Yang-Mills theory describes everything else except gravity. So they found this physical mathematical structure while asking one question, and it turned out to be the definitive answer. It turned out not to answer that question, but it gave a definitive answer to many other questions. So progress in physics is of many faceted, many different directions. And so that's what happened with string theory. String theory was constructed as this way possibly of understanding the strong interactions. Didn't really work for that. But it looks like it potentially could work. On paper, it works. We don't have any experimental confirmation, and in my estimation, are very unlikely to get experimental confirmation for it. But it seems to have a lot to say about the problem of quantum gravity. And so I thought, when I was a graduate student, I was interested in quantum gravity. String theory was already around then. I thought, I loved the whole thing of Einstein and his elevators and Bohr and his thought. I thought that to solve this problem of quantum gravity, we needed some really deep conceptual insight. And string theory looked like just sort of a jumble of equations. That's how it looked to me at that time. And I hadn't really paid much attention to it. And I thought it was a sort of technical exercise. But then I started to study it. I felt I should study it because it was relevant to the problem I was working on. And the more I studied of it, the more I began to realize that there were a lot of beautiful mathematical structures in there that possibly with some modification or whatever could be used to solve other problems, which it certainly has, and might, fit into quantum gravity in some way that we don't either don't fully understand or haven't verified experimentally. So that's when I started to learn about it. Now, interestingly, in the early 70s, so string theory is a very complex theory with many moving parts, all of which demand complete precision of all the other parts. It's a very cohesive whole. And one of the things, they were trying to use it to describe the strong interactions, and one of the things was that it was found that in order for it to really fully work, you had to have a particle in it that looked like it mediated the force of gravity. It's not happy. It's not self-consistent without gravity in it. And the people who were working on it weren't interested in gravity. They were interested in the strong interactions. And, the theory was under discussion for 5 or 10 years until Shirk, Schwartz, and Yonea came along and they said, well, wait, maybe we can't use this for the strong interaction, but there's this problem of quantum gravity, which very few people were paying attention to then. And however, what they believed was, at that time in the early 70s, was it could describe a theory with gravity and only in 10 dimensions. But it couldn't, there was no possibility of incorporating protons, neutrons, quarks, or anything like that. So it was thought to be something which in principle was incapable of describing the real world. And moreover, it was in 10 dimensions. And then what happened, and you asked me about how I got into the field, so I started thinking about this and discovered that there was a way that you could kill 2 birds with 1 stone. There was a way of curling up 6 of the 10 dimensions. And this used some very cutting-edge mathematics. And the mathematics of this was then and still is something of very active study. So there was a lot of synergy between the physicists and mathematics beginning at this time and continuing to the present. And you could do 2 things. You could curl up 6 of the 10 dimensions and make them undetectable to ordinary experimental probes, thereby leaving you with 4 dimensions that we could roam around in, consistent with our observations. And in the process of doing that, is a very natural byproduct. One can produce, in addition, all the elementary particles that we see. So all of a sudden, this was work I did with Kandelowitz, Horowitz, and Witten. And all of a sudden, string theory went from being a mathematical curiosity to an actual live candidate for which could potentially be the universe around us. It's a logical possibility that the world around us really is described by string theory, and if we had good enough microscope, we could see the little strings as we looked resolved to smaller and smaller distances. And that excited a lot of people. And that was kind of the beginning of the modern string theory, with a lot of people interested in it. You better ask me a question.
Yeah, sure. So you've already touched on some of the endlessly fascinating aspects of string theory. I mean, 10 dimensions, and then the 6-dimensional Calabi-Yau shapes that you alluded to. But for context for our listeners who are less informed of the background physics, I'd like to go way back to where you started and spend a bit more time of the inconsistency of quantum theory and general relativity that motivated your entry into the field. And so, as I understand it, though you'll, I hope, correct and amplify what I say, Einstein's theory of general relativity is extremely successful as a theory of gravity and the massive, whereas quantum field theory, and more particularly the standard model of particle physics, accounts for the other three forces: the strong force, which you've mentioned, and then the weak force and the electromagnetic force, and the microscopic. But that these two theories are incommensurable. And if this is correct so far, then maybe you could elaborate on why or how they're incommensurable.
Well, one of the great successes, quantum field theory, is, arguably the greatest, the greatest achievement of, 20th century physics, or maybe physics of all time. Certainly, if you count Nobel Prizes, I don't know what it is, 30, 40, something like that. And the many, many aspects of it. And it is the most accurate agreement between theory and experiment in the history of human thought. That is, there are predictions. Yeah, 14 decimal places. Yeah. The agreement, it's incredible. And they're, of course, chipping away at the last digits. And, to compute the 14th decimal places, you need big supercomputers. To measure the 14th decimal places, you need giant accelerators. And it just keeps agreeing. And now, but part of what led to the standard model, so there are the quantum field theories are theories which are consistent with quantum mechanics, which we can think of as, say, the uncertainty principle. They're consistent with the uncertainty principle. And at the same time, they're consistent with the principle of special relativity, which is that no disturbance, nothing can go faster than no message can be sent faster than the speed of light. Now, all of quantum mechanics and the Bohr atom and all that stuff in the early part of the 20th century, great experimental success, of course. That early part of quantum mechanics was largely developed in the period of a decade or two. And but all of that stuff was not consistent with the principle of special relativity, that nothing can go faster than the speed of light. And making those two things consistent turned out to be very hard. And it also turned out to be, you can't just write down any old theory and make it consistent, but there was an algorithm for wedding the two things, which is the subject of, I have a whole row in my office of textbooks on this subject of how you do it. And it's a very detailed thing. And obviously it's got to be detailed if it's going to somehow produce these 14 decimal places. Mm-hmm. And not any old theory can be made consistent. And it worked for the strong interactions. It worked for the electromagnetic and the weak interactions. And indeed, this consistency criterion, in the beginning of the 20th century, we didn't know about the strong and the weak interactions. And the consistency demands of putting together special relativity and quantum mechanics played a key role in narrowing down the possible theories. Okay, the first thing, but even before you have agreement with experiment, you need self-consistency. That is, you have to be able to, if you don't have self-consistency, you can't predict what the experiment is going to see. And self-consistency turns out to be our universe is a very weird place. And to find a self-consistent theory that describes our universe is very hard. And that played an important role, and it culminated in the Standard Model. But gravity was left out of the fun. It was never understood how to write down a mathematically consistent theory of quantum mechanics and general relativity. And this had two aspects. Well, let me say three aspects, three different ways, undoubtedly related, but three different ways that you could get into trouble. The first is, if you just take the sort of rules that were developed for taking a theory without quantum mechanics and adding the quantum mechanical sauce to it, which worked for the strong electromagnetic and the weak interactions, you get infinity. So if you took this seriously, you would say that the quantum corrections to the Earth's orbit around the sun are infinite. And we don't care what Newton said because the quantum effects change it by an infinite amount. Okay, that makes no sense, right? And that's the first problem. Wolfgang Pauli noted this problem already in the 50s of the Pauli exclusion principle, one of the founding fathers of quantum mechanics. And then the second one is, I guess the second one I would say came from Stephen Hawking's observation in the 70s about black holes. So gravity, Einstein's theory of gravity, known as general relativity, contains black holes in it. And Hawking famously showed that those black holes, a classical black hole, by definition, is a region of space-time where the force of gravity is so strong that nothing can get out of it without going faster than light. And nothing can go faster than light, ergo nothing can get out of a black hole. Now, but then quantum mechanically, there's a boundary of the black hole known as the horizon, the region. And quantum mechanically, the uncertainty principle of quantum mechanics says that everything is uncertain. And so the horizon necessarily has a quantum nature. And so you can't be too sure whether or not you're inside the black hole. And so things that are inside the black hole might get out. And that means that a black hole will slowly lose energy because we have to conserve energy. And if stuff is getting out, the black hole has to be losing energy and getting smaller. And Stephen gave a very, spectacularly elegant and simple calculation of what comes out. And he said that it looks like a kind of random radiation, hot radiation at some temperature. And what happens then is that the black hole shrinks and disappears, but but what came out of the black hole is unrelated to what went in. And that's a big problem, because in physics, the laws of physics assert, okay, now, by the way, they don't tell you this, but physicists believe firmly and absolutely in some completely outrageous things, unshakably, including myself. And one of them is that if you knew everything that was happening right now, we believe that we're all powerful. If we knew all the laws of physics and we knew everything that was happening right now, we would know everything about the future, and we could completely reconstruct the past. Not approximately, but if we knew everything and we knew all the laws of physics now, what was going on now, we would get everything in the future and everything in the past. No room for free will. No, it's the absolute thing. Okay, so I believe it, I guess. I don't know if I really believe it, but it's certainly a useful belief, and it's the operating principle of every physicist is that we're able to describe everything. If physics doesn't, the end of the movie inexorably follows from the beginning. And if this isn't true, if the laws of physics don't determine the future from the past, what does? Well, okay, I don't know how to think about what an answer to that question would be. So I just assume it's true. But according to Hawking, it wasn't true, because it was random. There's some random number generator of what comes out of the black hole, and you didn't know what was going to come out. You also can't run the movie backwards and figure out what was in, because it fell into the black hole and dissolved into nothingness. So that's pretty scary. And that's okay. So you could try to run with what Hawking said and figure out what we're supposed to say about how the universe behaves in the absence of deterministic laws. But people didn't make much progress on that. And for a variety of reasons, including insights gained from string theory, most people now think that somewhere there was an error in Hawking's argument and that the past determines the future. But this is obviously a problem in quantum gravity. Looks like an inconsistency coming out of quantum gravity, because it's saying that, we use black holes in quantum mechanics and we get results that don't make any sense. So by the way, this might sound like a bad thing, but it's not a bad thing. It's a good thing. It's what we all hope for, some puzzle like this, because that's where these puzzles are, the keys. They provide the keys to our next level of understanding about the structure of the universe. It's certainly been true historically, and many people, myself included, suspect that this quantum gravity puzzle, the black hole puzzle, are the thing that is going to, help us understand the universe. I mean, it's amazing how much we understand about the universe already. The uncertainty principle, black hole. It's incredible that the human brain could understand all that, and it's certainly exhilarating to be part of that adventure. But so we're hopeful that this problem of quantum gravity will be useful in that regard. And then the third problem with quantum gravity, and this one is a little not quite as sharp as the other two, but quantum mechanics tells you that everything is subject to the everything that can carry energy is subject to the uncertainty principle. And we now know that space-time, and I guess we've known for a long time, but space-time itself can carry energy. That's gravitational waves. And therefore, space-time is subject to the uncertainty principle. It's very hard to understand what exactly that means. And,
Right.
and literally when we teach about quantum field theory, we go to the blackboard. That's our framework. We write down the equations. Space-time is the blackboard for our, and it's fixed there. And it's the blackboard on which all the particles and fields of nature interact. And but now in quantum gravity, general relativity, the blackboard itself is getting fuzzy and joining in the fun. And so, what is that supposed to mean? What do we get to hang our hats on? What's our starting point? If the blackboard is itself part of the circus. So that's what, these are very it's conceptually challenging and it's mathematically challenging.
There are about 100 places where we could go into more detail, probably more. Jitters of microscopic space, for instance. And I'm actually somewhat surprised that you think the sort of Laplacian idea of determinism is really so crazy, or maybe you think it's crazy to maintain in light of quantum indeterminacy. But okay, you've sort of alluded to Bekenstein-Hawking entropy, and that's some foreshadowing, though, of what hopefully we'll get to. But just as another maybe concrete example of where things break down, and since, as I just said, I know you've done a lot of work in this area, how or why do the singularities, though maybe there aren't singularities, at the center of black holes stand out as something like paradigm cases where we're really left in the lurch because of the incompatibility of QM and general relativity?
Well, I don't know that a singularity per se is, I don't know that is the heart of the problem. A singularity per se is, some of the there's a classical singularity inside a black hole. And in principle, you might just think that, all equations are approximate because we don't know all the laws of physics. As I was saying a moment ago, we think there are some exact equations. We just don't know what they are. And so a singularity in principle might just be a sign that we're using some approximation to the equations, which needs to be corrected. We need to take into account more terms. So that in and of itself is not the most serious problem. The more serious problem in quantum mechanics and black holes is the one I said about the evaporation and determinism. So this seems to be, and importantly, you might ask the question, well, maybe there it's because of some approximation we're using. And that's a very important question. Are we getting these seemingly contradictory results because our approximation isn't good enough? And that might be right, But Hawking did give what seemed to be a very robust argument that our approximation was good enough, that was addressed. And you never have to go to the singularity to derive the contradiction. And so the singularity, it's behind an event horizon. We can't see it. So yes, it's an important thing to think about, but its final role is not clear to us now.
So I'm sort of surprised by this answer, which means that I'm wrong about something, which is totally to be expected.
Oh, you might get a different answer from somebody else. That's the great thing about.
Can I try to rephrase or expand on my question and see if we find something else? So the singularity, the black hole, is predicted by general relativity, and it is an extremely massive object, but it's also microscopic. And the notion...
Well, the issue of a singularity, of course, comes up before quantum mechanics. So classical black holes have the singularity in the middle of them. And so there certainly is a question of how we're supposed to think about that singularity. And people are bothered by it to different degrees. Einstein was very bothered by it and thought that black holes didn't exist because the singularity was impossible to actually produce. But yeah, go on.
Well, I guess another problem, and then getting back to the Bekenstein-Hawking entropy, my understanding is that one of the reasons that black holes aren't expected to have entropy in the first place is that the measure of disorder is directly connected to the amount of possible microstates of any given configuration. But if a black hole is as small as it is predicted to be, then there's only one possible microstate. So it shouldn't have high disorder at all. And that's another place where the microscopic and the massive really conflict.
Right. So there's a famous phrase due to John Wheeler that black holes have no hair. And this is something you get from the Einstein equation. So if you have a bunch of matter that gets drawn together by gravity, it forms a star. There are many, many stars in the universe, and there are presumably many, many with the same or almost the same mass as our sun. But each one of them is different in myriad different ways. They'll have different chemical compositions. So if you zoom in with the microscope, you'll see different atoms moving in different directions. And so they differ in every one of them is completely different. A black hole is not like that. Every black hole with a given mass and spin, they can also have spin, is exactly the same as a solution to the Einstein equation. So that is, John Wheeler described that by saying black holes have no hair. And since they're all exactly the same, not just approximately the same, but like exactly the same. And this statement can be made mathematically precise, and there are a number of mathematical theorems around it, which give more heft to this statement. So if they're all the same, if you want to store information in your computer, you need a bunch of gigabytes, which could chips, which could be flipped up or down, and you could choose flipping this one up, this one down, many different configurations of a computer. That's how you just store different information in it. But how do you store it in a black hole if every black hole is of the same mass, is exactly the same? And that was in very sharp contradiction to an indirect inference of the work of Hawking and Bekenstein, that black holes have a temperature, and things with temperature and energy, as we learned back in the 19th century, they have something called entropy, which is just they have some gigabytes in them. They have some storage capacity. They have to have many different configurations. If you have like a hot steam in a pot, there's a lot of little water molecules, H2O molecules bouncing around in there. And the heat is related to the fact that they can bounce around in many different ways. That can be made very quantitative. And so to have heat, you need a lot of different possible configurations. You need gigabytes. And so Hawking's calculation applied that black holes have an entropy, and there's a very precise formula for it. The classical calculations say that they don't have an entropy, so that's a puzzle. And that puzzle, you were probably about to ask me this, that puzzle was mathematically solved in some cases in a very robust and detailed way using string theory. And so that was kind of a turning point in our thinking about black holes. That's what Vafa and I did.
In the interest of eventually, quickly, hopefully getting to string theory, there was one other motivating factor that you didn't mention when I initially asked you why you got into string theory, because you were interested in reconciling quantum theory and gravity. That I'm curious about, because I know it's a motivation for a lot of other people who work in string theory. One person that comes to mind is Andre Linda. I'm not sure if it's Linda or Lindy here at Stanford, but that is fine tuning. And I didn't pick it up on looking at any of your papers, but how do you think of the apparent fine tuning of the universe? Do any particular aspects of this stand out for you? And is it at all a motivation for your pursuit of string theory, or you don't really think about it?
Fine tuning. Which fine tuning are you talking about? The cosmological constant or the?
Not just the cosmological constant, but why the forces have the strength that they have, the particular assortment of subatomic particles we have, and if any of these things were different. Some are more sensitive than others, life wouldn't arise. So there is a question of why things are the way they are, why we find ourselves in a universe that supports life like us.
Yeah. So I guess this is, this is an old problem. I think Dirac called it the large numbers problem. Ratios of, if we take the ratio of the Planck mass, which is the mass of a black hole whose Schwarzschild radius equals its Compton wavelength, which it's sort of a basic mass scale in physics, to the mass of a proton. That's a huge number. It's like 10 to the 20 or something. And then we can take the ratio of that to the cosmological scale, another huge number. And so when you have these numbers that are so big, if you take a piece of paper and write down the laws of physics as we understand them, they're going to be ratios of numbers which are, 10 to the 20 or more, in case of a cosmological constant, even more. And that, that demands an explanation. We'd like to know why. Why is the ratio 10 to the 20, not 10 to the 15, let alone 5? If you throw a couple, if you grab some, what's a good example? Most numbers would ordinarily be 1. If you balance your checkbook, if you write checks and you spend money at the end of the month, the difference between what you earned and what you spent is not going to be, hopefully it's a number of order 10 to the 20. It might be 1. It might be a factor of 10. It might be a factor of 100, maybe even a factor of 1,000. But it's not going to be a factor of a trillion. And if it is, you'd say, wait, I think I made a mistake in my computer program or however I calculated this. But we're pretty sure there isn't a mistake, that these numbers differ by some huge amount. And we'd like to explain that. Now, there's been a lot of brilliant work coming up with explanations why it would be normal and expected for this to be true. Some of it involves supersymmetry. Some of it involves the Anthropic principle. And I think it's fair to say that despite the first of all, the huge amount of work, that's far more work has gone into this question than into the problem of quantum gravity, far more. And so, and largely because it has to do with things that we measure, and we might think there could be some prediction or something coming out of it. I think it's fair to say that the reward to effort ratio in this enterprise has been extremely low. That despite the clever ideas and approaches and so on and so forth, we just don't understand it. If I had an idea to explain, so that's why this is why science is not a science. Science is an art. If I had an idea how to explain why the cosmological constant was so small, I'd stop everything I was doing and I'd cut off this phone call and I would go and work on it. I don't have an idea. And my own view, though lots of people are working on it, nothing looks very promising to me. And of course I could be wrong. I'm just guessing. I don't think you alluded to the Anthropic principle. It could be right. It's not a logically inconsistent thing, but it not only has to be right, you have to be able to do something with it. You have to be able to make a prediction. It's not enough to explain something you've already measured. I'm not saying what's right and wrong in science, but as a I would say incontestable sociological fact. If you come up with a theory that explains something that has already been measured, that's not enough. To confirm the theory, you have to make a prediction, tell somebody to go to measure it, and then they have to come back with something that agrees with you. Some famous example of this was the precession of Mercury's perihelion, which was measured by Leverrier in 1859 to be off from the Newtonian prediction by 1 part in 100 million. And, the planetary orbit, Newton was almost exactly right. He was off by 1 part in 100 million, right? And you got to admire these guys. Okay, so that sat there, and somebody said, okay, it's only 1 part in 100 million. There's probably some dark matter, which, by the way, is now used to explain everything that we don't understand. There's probably some dark matter.
That or aliens.
That or aliens, right. There's probably some dark matter floating around out there that we don't know about, and it's moving, it's affecting Mercury. That's the 1 part in 100 million effect. And they convinced themselves that this dark matter theory was correct. So when Einstein came along and gave the real explanation, nobody was interested. They're like, are you kidding me? You're telling me that space-time is curved and your evidence is that Mercury's perihelion is off by 1 part in 100 million? But then they listened when he said, yeah, that's what I'm saying. And if you look at the next solar eclipse, you watch the star go by, its position is going to move in the sky. And Newton would have told you it's going to move this much, and I'm saying it's going to move twice as much. And that turned out to work. So that was a prediction, experimental prediction. So the anthropic principle, maybe it's explained, because if you explain something that you already know, that's already been measured, people are suspicious that you've cooked the books. That you went out and searched for it. You're not finding something new. That you went out and cooked the books. You cooked the books. So Einstein knew he didn't cook the books, but he wasn't able to convince anybody else that he had until he made a prediction. So I don't see the anthropic arguments leading to a robust, measurable prediction that will persuade so I don't think it's going to go that far. I don't really know whether I think it's right or wrong. They tried to use the anthropic principle to explain the periodic table. That if the elements didn't have just the right weights, you wouldn't be able to have life, and so on and so forth. And this was the reason for the different atomic weights. And then, of course, you had the Bohr atom, nobody was interested in the anthropic principle anymore. So I think it's an important problem. It's not what I don't want to dismiss the problem. Every once in a while, I think about it to see if something I've learned in the last 5 years triggers some approach to it, but I don't sit there and bang my head against it. I bang my head against the black hole problem, because that one keeps it moves when you bang it, and it seems like we keep learning more, and I have a feeling that we're making progress on it. And I think that would be the one thing that everybody who works on it would agree on, that we're making progress. They wouldn't agree on what the progress was, but they would agree on a few things. They would agree on a few things, but they would disagree on
many things. Well, again, hopefully we'll get there, and I can ask you about how different people would understand the progress. But for now, or at least 20 or 30 minutes ago, you mentioned that our universe is a very weird place. So returning to that, and at long last now, the basics of string theory. And I'm going to leave M theory and 0/2+ dimensional brains aside for now, unless you think it's important to introduce, though. But for the time being, just one, what is a string? And then how basically are they to be reconciled with the already extremely 14 decimal point successful standard particle model, or to put it in other words, what's the relationship between strings and point particles?
Well, so one of the interesting things about string theory is that it can be described from many different equivalent viewpoints. There are many different ways of arriving at string theory. It's kind of like all roads lead to Rome. People have tried to construct theories which general, and there are many different descriptions of it. But the first one involves strings. And it's an odd thing that we still call, that it is still called, especially in the general public and general discussion, that this big theory is still called string theory. Working theoretical physicists like myself don't use the word in quite the same way that it's used in the press, because the part that is directly related to strings is only a small piece of this big mathematical structure of the space of possible quantum field theories and general relativity and black holes and all these different ideas, which are not separate ideas, but are tied together in many different beautiful ways, often involving profound mathematics. And so string theory is just a little corner, but somehow that corner has the whole enterprise of the majority of what theoretical physicists and mathematical physicists have been doing for the last 40 years has been lumped together under the heading string theory. Okay, but it did start as the idea that if you replace, in quantum field theory, which is the theory that's been tested to 14 decimal places, the basic object is a quantum particle which moves around and interacts, and they scatter electrons and protons, they make up atoms and everything. So that these particles, actually, if you had a very, very powerful microscope, you could see that they aren't actually point-like objects, but they're little loops of string. And loops of string, and this weirdly solves the infinity problem. This makes quantum, this just replacing, well, in a very specific way, there are very prescribed rules about how you do it, but replacing the notion of a particle with a string leads you to a theory without the infinity problem that Pauli had. So that's what a string is. Now, a string can do different things, right? If you have a little string, so particles don't have much structure. They might have a spin that could point up or down, or a charge, but they don't have a lot of structure. But strings can do all kinds of things. They can, vibrate in a figure 8, or they can do this, or they can do that. And if you look at it from far away and unable to resolve that fine structure, what has been amazingly shown is that the strings can, to the observer who can't see the fine detail, the string can masquerade as any one of the particles in nature, the electron, the quark, the neutrino, the photon, even the graviton. So that's a really very striking mathematical fact that the string, the costume closet of the string contains costumes which look like everything that we've actually seen. Now, this doesn't mean that the world is made of strings. It just means that it's a logical possibility.
And I think you mentioned that when we were talking about point particles, they don't resolve into anything. They just look like points, but they have some other qualities like mass and charge and spin. And I'm wondering how the mass and the energy, for instance, of a string's vibrational pattern are connected, so that we end up, if it vibrates in some certain way, we have a particle with a mass. If that question makes enough sense.
No, totally. Yeah, I wanted to use another analogy. It's like, a guitar string, right? You pluck the E, the top string, the E, and it makes a certain note, and then you put your finger on the fret and pluck it. It makes another note. So one string, guitar string, vibrates, interacts with the air, sends out sound waves. One string is capable of sounding different, can make many different sounds. In fact, if it were a really good string, it could make infinitely many sounds, because there are infinitely many, a perfect string. There are infinitely many harmonics. It could make infinitely many different sounds, higher and higher harmonics. Similarly, a fundamental string in string theory, depending on how it's vibrating, interacts differently with light, and it will look different. So that is how a string can look like different particles. Now, you just asked me, how do we relate these things? Well, there's a formula. It's a complicated formula. It's a very, when you teach a course in string theory, they have to have had quantum field theory and relativity beforehand, and then it's a couple of weeks before you could write down that formula. But there is definitely a formula which tells you exactly what the string does.
Okay. And there are two deeper questions here that I have. So I can understand how, so bosons are the sorts of particles that carry what we think of as forces. So photons are the bosons for the electromagnetic force. And I can understand, given the picture you've just described, how a vibrating string will manifest as a photon. But something that I don't understand is, if in the standard model, the Higgs boson is what gives particles their mass, how a string independently of the Higgs boson, so a string that will become an electron, can have a mass independent of the string that represents the Higgs boson? Or, and again, maybe this question might be confused, because I haven't read anything about this question. It's just something that occurred to me as I was reading and thinking. But maybe you can elaborate or tell me that I'm just mixed up somewhere.
Well, I don't think the answer to this question is very different in quantum field theory than it is in string theory. In other words, there's a limit of string theory. There's some limit in which you just look at you sort of think about the theory on longer distance scales where you can't see the strings, and then it reduces to quantum field theory and what we know and love. And if you wanted to explain how the Higgs bosons give particles a mass, it wouldn't buy you anything in string theory. So string theory can have Higgs bosons, and the Higgs bosons can give masses, but those are all, the basic reality in string theory would be the strings, and other things are approximate, right? So, and they're only in some approximation scheme do they make sense. And so, if you were trying to answer this question, the answer wouldn't really be different. It wouldn't use string theory. It would just use the usual ideas from particle physics. You would reduce the string theory system of equations to the particle theory ones, and then you would just sew in the particle theory explanation.
Okay, and then my last mass-related question is, the mass of the particle that is a string is determined by the vibration of the string. Does it just make no sense to ask what the mass is of a non-vibrating string?
No, that question makes sense. But it would depend. I mean, I'm taking a little bit of liberty here in translating your questions into a more precise mathematical one. But I think that you could say that the massless particles in nature, like the photon, the graviton, they're examples. They can be thought of as examples of strings that aren't vibrating in their kind of lowest energy state.
And then, as I understand it, in the standard particle model, point particles like the electron don't decompose into anything. They're primitive. Does it also make no sense to ask what strings are made of? They're just primitive.
Yeah, that is a very interesting question, and it ties into something a little bigger, and I think it's the kind of thing you're asking me about. So let me kind of enlarge your question a little bit and then answer it. So, of course, there's been a history in theoretical physics of the so-called reductionist program. So we started out with, fluids and gases, and then we learned that those were made of molecules, and the molecules were made of atoms are made of protons and electrons, and then protons are made of quarks and gluons, and so does this process ever end? So first of all, this was kind of, many people would view this as what the frontiers of theoretical physics are. Understanding the laws of nature at shorter and shorter distances. And some people, indeed in 1985, when No, so in one sense, the answer to your question is no. The string theory can't be made of, strings can't be made of other things, because there are two ways of saying this. One is, if they were made of other things, we'd have to correct the equations somehow. And the consistency of string theory is so exquisitely precise and finicky that we can't modify them in one iota. No other theory in the history of physics was like this. If you take in quantum field theory, you can have 3 quarks, you can have 5 quarks, you can have neutrinos, more neutrinos, whatever. You can add more stuff. Maybe some stuff you thought wasn't there. In string theory, there's this. It's a kind of an all or nothing proposition. You can't monkey with it. So this could potentially mean, and there's another problem that you would have, is that so we did this computation of the entropy of a black hole using string theory, or in stringy universes, which our own may or may not be one, but at least in some stringy universe, there's some way of making sense of what Hawking did, Bekenstein and Hawking. Now, we got very precise agreement. So you could say what they did was predicted how many gigabytes there are in a black hole. And Vafa and I actually counted them, and they agreed. Now, if the string has more structure, there would be more gigabytes, right? More configurations. And so you'd be in big trouble. So there are many different ways of saying that the answer to your question has to be no. This very different, there was never an argument like this in any other theory that you'd reach some kind of end. And that was, I guess, that was philosophically very interesting. And so many people thought, okay, we've reached the end, and I was not one of them, and I'm not, but many people say, okay, with string theory has the potential that it's the end of the reductionist program. We learned that, molecules were made of atoms, and atoms made of electrons, protons made of quarks, and finally we reached the end and we're done. And that wrapping up all of physics is maybe its sight. Now, I had a lot of conversations with Steve Weinberg, probably the most eloquent champion of the reductionist program. That this is what physics is, and somehow, okay, it could be a really wonderful man and a great scientist who sadly passed away last year. And okay, it could work that way, but it doesn't feel right to me. It seems there's always one mystery begets another mystery. And would we understand everything there is to understand about string theory? There'll be support questions that we'll have. And there's lots of things left hanging. How did the universe begin? Why are we in 40? Lots of things left hanging. And so I said to Steve, why do you think we're ever going to find the end? I mean, aren't we just going to have more questions? He says, what would it even mean to know all the laws of physics? That just sounds really strange. And he said, well, that's what they used to say about the Nile. Never going to find the end of the Nile. They explored the Nile. Everybody thought that there was no end to the Nile. It just went on forever. And then finally they found it. That was it, And so we don't know maybe we'll understand everything about physics. That's where the word which I don't like, theory of everything. Could this really be a theory of everything? I don't know. But for now, we're not in trouble. For now, there's lots of stuff we don't understand. Whether it could happen, we don't really know. But there's another important wrinkle in this, independently of that, is while you can't, this was an interesting wrinkle, and it's a good example of how string theory forces you, its equations kind of drag you along and open your mind to different ways of thinking about things. And so what turned out to be, we found is that actually string theories are not the fundamental entity of string theory. They're one of many ways of describing some big structure. So so there are things that you can do to string theory to make all the strings disappear, and you're left with some other kinds of objects, brains and other kinds of weird objects. And so strings are not fundamental in string theory, and we don't know what is fundamental. It's like we can start in Boston and describe the road system by giving all the how far you go on each road and how many turns you take to get all the other cities in the United States. But that doesn't mean that Boston is fundamental. We could also start it in Pasadena or Palo Alto or St. Louis or whatever, and that doesn't mean that Boston is the end of the world or the beginning of the world or anything like that. It's just where we started describing from. And strings play that same role. And what is I think even more profound is even the idea, and this is a little harder to explain, but related to the holographic principle, that somehow the laws of physics, the old way of thinking is somehow the laws of physics are written at short distances where we can't see. And then we work out their consequences for longer distances. Who said that's how it has to be? Maybe it's the opposite. Maybe the laws of physics take their simplest form if you describe them out at infinity and work your way back in. And in fact, we're being led to that kind of thing. So just as we thought we were getting to the end in some sense, of course, we have to get to the end, we also have to do experiments. That's important. The theorists are kind of racing ahead of experiment now because experiments have gotten so difficult and expensive, not because we don't think they're important. But we do what we can, and it looked like there could be sort of an end to the laws of physics in the form of strings, but then it kind of blew up into our face and sent us back to long distances. And who knows, maybe this problem you mentioned an hour ago about the cosmological constant, why is it so small? There are things we don't understand at the biggest distance scales too. And maybe we have to totally reformulate. That's my kind of hope, is that the cosmological constant problem is an indication that there's something we really don't understand about. It's not just short distances we don't understand, but the biggest distances, or we understand the distances we live in. And we have trouble both understanding very short distances and very long distances. And maybe those are somehow related. Okay, I should be saying that's not a podcast. I mean, this is all things I think about late at night. But, I don't Yeah, but anyway, I don't think we're anywhere near the end. Really, I think we're at the beginning, And
Well, a few things, or at least one thing is that you mentioned Weinberg. He's one of those dream guests that, very unfortunately, I just missed by starting my show a little bit too late. But two things you said that are really important. That one, the theorist is racing ahead of experiments, and the second thing is that the consistency of string theory is so sensitive. As you put it, it's all or nothing. And the work with Vafa you referred to, counting the gigabytes in a black hole, was a huge advance for string theory and is strong evidence for the theories, M theory maybe is what I should say.
Right. So it's very important.
Value.
If you're in a field, okay, the best thing, of course, is to have an experiment. But if you don't have an experiment, it might be good to just go home and cry. I'm not going to just go home and cry. I'm going to sort of do what I can. And some people will think no problems of this magnitude could be solved without experiment. They might be right, but we're trying. And you don't know what the future of science is going to bring. My view is you don't know what the future of science is going to bring, how it's going to proceed. People use the history of science to justify various approaches and stuff. But again, so many different things have happened that you could. So everybody, I think what it takes is every curious mind looking at the facts before them, thinking about how they can contribute, what they can do. And we just have to blanket all possible approaches and we'll get through eventually. And we don't know where the break is gonna, the break is gonna come. Sorry, what was your question there?
Well, I didn't get to it, but I'm about to get to it. What I was going to say is that the solution or the resolution to this Bekenstein-Hawking black hole entropy problem is immensely valuable, but it doesn't directly demonstrate the existence of strings, which is still far from, my understanding is that it's far from generally accepted. What I've heard from a lot of astrophysicists on an unrelated note is with regard to certain extraterrestrial speculations, they say it's not aliens until it's aliens. And I have the sense that a lot of physicists have something similar in mind. They just think it is not strings until it's strings. And you said a few minutes ago that if we had a powerful enough microscope, we could observe strings, but unfortunately we don't have that microscope. So even though this might be purely hypothetical, given constraints of funding or energy, how might strings be directly observed or detected?
Yeah, you're going to get very different answers to this question from people that you interview, and I think I don't think my view is really I have kind of a minority view. And so what happened was, string theory as a theory of quantum gravity and so on, as we discussed at the beginning, was discovered in the early 70s. And then, but it was thought that it, in principle, was incapable of describing the real world. And one way of summarizing what happened in the 80s was it was found in around 85, where there was a kind of big explosion of interest, was that in principle it could actually describe the real world. And not only could it describe the real world, but it wasn't very much of a stretch. You didn't have to stand on your head. The structures that we see in the real world come very naturally out of string theory. So it's always a good thing. You don't want to have one theory which solves every time you have a new problem, you make a new theory. You want a new theory to solve a number of problems. You should be getting out more than you put in. So string theory, you might have thought in the 70s it was constructed, some structure that was dictated to solve this infinity problem in quantum gravity. But now if that same structure also produces quarks and leptons and parity violation and generations and all that kind of thing, then that's exciting. And then, of course, it's also, to link back to what you were saying a minute ago, it's exciting that the same structure also can solve the problem of counting the gigabytes. So one thing is you're getting out more than you put in. Now, in the 80s, when it was realized it could describe the real world, there was a lot of excitement, and we didn't really understand how many ways. One way of saying this is we didn't really have a very good understanding of how many possibilities there were from getting from 10 dimensions to 6 dimensions. That is, I'm simplifying a little bit here, but how many Calabi-Yau spaces there are. And if there had been, so when I first realized that Calabi-Yau spaces could be used to get string theory from 10 dimensions to 4 dimensions, I didn't know very much math then. I was actually friends with Yau. I hadn't really worked with him, but we were friends, and I remembered some things he said. And I knew that there was only one Calabi-Yau space in 4 dimensions, but we needed a 6-dimensional one. And I went to the library and I took out his paper, which I could barely read. I didn't know any algebraic geometry then. And I saw that there was one Calabi-Yau space that was 6-dimensional. There was only one mentioned in the paper. And I thought maybe that was the only one. And if that had been true, there would have been a huge amount of uniqueness in string theory. And there is, in some sense, uniqueness, but before we published our paper, Yau had told me he thought there were tens of thousands of them, and now the number and kind of cousins that can also be used has gotten enormous. And so there is no obvious way to experimentally verify string theory, short of building an incredibly powerful microscope and seeing them directly. Now, but hold on a second. So people didn't give up on that idea that you could somehow make direct predictions from string theory. I gave up on it. It seemed unlikely. Rational people that I would disagree with, but I don't think they're stupid. I just don't think that they're balancing the facts right, could disagree about whether it will someday be possible to make predictions from string theory. I don't think so. I don't think you could get lucky. You could find some generic, imprint from string theory. But I gave up on the idea in 1987. So I haven't thought since, and then I was in a very small minority. But now lots of people would agree with me. So I don't think that string theory is that we're going to measure strings. Yet, I mean, you can ask me, why am I working on it? I can answer that question. But I don't think that we're going to. I'm glad that other people are trying to do it. I don't think it's stupid to try to do it. If nobody else were doing it, might feel obligated to do it. But I think it's a losing. I work on problems I think I can make progress on, and
right.
I don't think making experimental contact, sadly, is going to be possible for string theory. And I think we don't know what string theory, how it will fit in. And my feeling, and also there's I think a false dichotomy out there that string theory is either right or wrong. And I don't think it's a black and white thing. The real question is whether string theory is useful and whether we've learned good things about it, from it. You learned useful things from it. And I want to go back to what the example I gave in the very beginning of the Yang-Mills theory. Yang-Mills theory was wrong. We know now it's wrong. It does not explain the relationship between the neutron and the proton. It explains everything else. Yang and Mills didn't mention that. But, so it explains everything else. They didn't quite see how it fit in. So I think there's plenty of room, and it has already happened to some extent, that string theory that the space of possibilities about how our subject might develop is really big, and we can't map it out now. And we're trying to find problems we think are important and interesting, like the black hole problem, and try to make everything fit together and explore the space of possibilities. And it's a huge, it's a massive undertaking. I like to talk about black holes. I'm very interested in black holes, obviously. Schwarzschild found the black holes in 1915. It took 100 years to see them. It took 50 years for people to be convinced they exist as mathematical objects. Another 50 years for the world to, really believe that they're up there in the sky. We're still struggling with their quantum nature. So these problems are big problems. They're exciting problems. They're deep problems, but they take a long time, and we don't do very well. If you had asked the founders of quantum mechanics what quantum mechanics was good for, it's too bad nobody did. But how quantum mechanics, how it's changed the world, the technology, how it fits in together with relativity, it's a wild story that they wouldn't have dreamed of, in the 10s and 20s, the early part of the 20th century. And I think the way that we'll look at string theory in 100 years will be very different. And by that, I mean this whole big body of knowledge that we call string theory. In 100 years will be very different than how we look at it now. But I would bet a lot that it will be important, that it will be a piece of the puzzles that we have put together. That I can prove it, but I'm betting my life's work on it.
Well, I have a couple of things to say. One, you said I might ask why you choose to work on string theory given what you've just said, but I think I can answer that myself, and you can tell me if I'm wrong. But given what you said earlier, you chose to work on string theory because it's a tool, and we can see how that plays out in your career. I mean, it solved or resolved the Bekenstein-Hawking entropy problem that had eluded more classical or quantum approaches to physics for 25 years. And this isn't a new approach by you, this sort of instrumentalism. I mean, Aristotle was an instrumentalist about like geometrical figures for geometers. You didn't have to think that this was a real sort of Platonic thing that you were drawing or aiming at.
Interesting analogy. I haven't heard that. Yeah. Nice analogy.
To be able to use it. Or Leibniz, for example, in the calculus, he did not believe.
It's very hard for us now to think of triangles as not being real, but yeah, that's a very interesting. It must have seemed that way back then. Yeah, what are these things?
I don't think that they're real. I think it's probably the dominant view among philosophers of math that they're not real. I mean, that there are
triangles are not real.
Well, in a Platonic sense, I mean, so most, and then I would think that most philosophers of mathematics who do believe in mathematical objects sort of construe them as sets, and that sets have a Platonic existence. But the other example I was going to say, Leibniz, he didn't believe in the existence of actual infinities or these actual infinitesimals, but they were a tremendous tool for solving mathematical and physical problems. And it's similar, I guess.
That's a great analogy. That's a great analogy. Yeah.
Good. I'm glad. But you can't directly test the existence of a string, or you don't think that will be the case, but they're incredibly useful for solving these outstanding problems.
I think it was my colleague Subir Sachdev who actually took my course when I was teaching string theory, and then later went on and used ideas from string theory to solve some problems in condensed matter physics.
That's great.
Yeah, so he solved some problems in condensed matter physics, and you could have solved them using known techniques. With hindsight, you could have used other methods, but you never would have put it together that way, sort of insights from string theory. And I think it was him that said string theory is the calculus of modern theoretical physics. You know, it's a tool. It's a set of mathematical relations that is an indispensable tool for many enterprises in theoretical physics. Making your analogy to Leibniz more precise, yeah.
Oh, great. Well, toward M theory, brains, and then the Calabi-Yau spaces that just came up again, one of the more unintuitive but thrilling aspects of string theory is that it requires more than the three macroscopic spatial dimensions we're all familiar with in everyday life and that fourth temporal dimension. But why does it require more dimensions, and how do you visualize them? How many are there? And again, I imagine that, or I suspect that for at least a brief period, we can leave M theory and the potential of 11 dimensions aside, unless you think it's a worthwhile complication to bring in now.
Interestingly, I think that question only has a technical answer.
Okay.
You ask the question, can I, string theory is a set of rules one of the ways that modern physical theories are formulated is there are many kinds of questions you could ask, but one question you could ask is, if I throw an electron and a proton at each other and they interact, what comes out? That's a question the laws of physics are supposed to answer. And in fact, it's widely believed that if you knew the answers to all such questions, like any set of incoming particles, throw them at each other at different velocities and so on, what will come out? It's widely believed, that's the so-called scattering problem, that if you know the answer to every scattering problem, you know everything. That's one way of writing down all the information. And that's how much, that point of view sort of started getting a foothold sort of in the 40s maybe, or 30s even. And so you can ask, but if you want to talk about gravity, you have to include in the list of things you scatter gravitons, which are the particles of gravity. And so if you could give the rules for scattering amplitudes involving gravitons, in some sense, you know everything if you give those rules. And so string theory was an algorithm for solving the scattering problem for anything, including gravitons. And you could not get self-consistent answers without either directly being in 10 dimensions or secretly being in 10 dimensions where you curled up some of them. It's a technical answer, but it's interesting. So, self-consistency drives us to it.
No, that's good. Because I was going to ask, why string theory as it currently exists makes extra dimensions necessary, or alternatively, why would it be useless to search for versions of string theory without these extra dimensions to preserve our spatial intuitions? But you've already given the answer, which is that consistency is the constraint, and that's why they're necessary.
And so that's good, right? Consistency is a good thing. We'd really like more of it. What people were so high with how far we got with consistency that, some people, that there was a kind of hope that started in the mid 80s that I don't think really, it sort of lingered on to around 2000, that somehow, if we understood all the consistency constraints, that there would just be one theory that made sense. I don't think many people are pursuing that idea anymore, but it was something that was on the table. Of course, that would have been amazing if it were true, but doesn't seem to be true.
One dimension, no. Well, I guess I have to say the pun was intended, as I chose that word, is of the question as I initially put it that I don't think you answered is how you visualize because you do a lot of work visualizing, like with the Calabi-Yau spaces, visualizing these things. So how do you visualize the additional 6 dimensions, and are they, maybe this is a good place to start, are they also analogous to one another in the same way that our 3 macroscopic spatial dimensions are somewhat analogous to one another?
Yeah, they are. Um, I do a lot of visualizing, but visualizing has its limitations, and ultimately, what falls back to the equations, which the equations can have much more information in them than any pictorial image that we can carry in our minds.
But so what do the curled up dimensions, how small are they? How can they be envisioned for people who haven't encountered the idea before?
Well, the natural size for them, and there's kind of two ways you could ask the question. If you just kind of say what would you generically expect? You'd expect that the size of the extra dimensions is 10 to the minus 33 centimeters, which is a billionth of a billionth of a billionth of it. It's tiny, right? That would be the natural size. Then there's a very interesting question of, okay, but could it logically be bigger? And what is the actual experimental? Forget about what's natural. What does, after all, there are lots of things in our universe which aren't natural. We started out discussing that. The size of the cosmological constant, the Higgs mass. So maybe the dimensions are much bigger than you would naively expect. Just using Occam's razor. And you can ask the question, how big could they be without having a conflict with experiment? We know that they're not a meter across because then we just see them. We could look in 4 different directions instead of 3. And in one of them, if it were small, if it was a circle, we'd see the back of our head, that doesn't happen. So they're not a meter, but how big could they be? Well, surprisingly big. So my Arkani Ahmed Diwali at Demopolis showed a long time ago. I think that was late 90s, maybe. When was that paper? And also Lisa Randall took another, and Robin Sundrum took another kind of take on this. That surprisingly, the experiments allow them to be big, so big that it's not impossible we could see them experimentally. Now, it could happen. It could happen that and there have been experiments done which put more and more stringent bounds. It's been, over the years, it's been shrinking. The experimental upper bounds on how big the dimensions could actually be. And I don't think they're going to, it's important to continue these experiments because we have to do everything we can. And these are really great experimentalists who are doing this. But I'm not betting that they'll see them. I think extra dimensions could be there. They're a logical possibility, but there's no good reason they would want to be so big.
I know that we're talking about dimensions right now, and not strings or brains of other dimensions. But you mentioned this idea of you could look and see the back of your hand, and for whatever reason that brings to my mind, and since we were talking about the possibility of observing strings, that I don't know if Witten, who is the my understanding, because I'm not really in this field, he's the physics genius of our age, has suggested that it's a possibility that there could be strings out there that are large enough on a cosmic scale that we could observe them through a telescope, because the levels of energy at the Big Bang could have produced them. So that's a possibility.
It's a possibility, right? And indeed, there was an exciting moment. There was an exciting moment when astronomers thought they'd seen something like that.
Oh, really?
From lensing of stars. That was after Witten's paper, I think. And that's enough, that could have happened. It's not logically precluded. They could have measured the extra dimensions. They could have seen strings stretching across the sky. All those are logical possibilities. It's not precluded. And I think it's a sort of logically important aspect of the theory that you could get evidence for it. It's, there's some theories that, they don't make any predictions. They're interpretations. There's no experimental there's no experimental way to verify, the Copenhagen versus the many worlds interpretation of quantum mechanics. So it becomes more philosophy than physics. So it's important that there could be a measurement that tell you that string theory was actually right. They could suddenly pop on our plate someday and we'd find them and we'd be very happy. But I'm not betting that that's going to happen. Yeah.
Well, returning to our thread, pun intended again, you have played an instrumental role in developing our understanding of Calabi-Yau shapes, which have come up a few times, and which I think also might help make sense of what these 6-dimensional spaces are like that we're appending to our more...
Wait, those are the Calabi-Yau manifolds. Those are the 6-dimensional spaces.
Right. I guess I meant they might help us make sense of how to visualize them. But maybe you don't think so. But I was going to say is there talking about the geometry, but is there a simple way of explaining the basics of your work here and the relevance that these shapes have to string theory?
Well, I can say something about them, but first of all, I think you can describe spaces by equations. So the simple example of that is if we have a plane labeled by X and Y, that all the points obeying X squared plus Y squared equals 1 lie on a circle. So that's one way of describing a circle. You start with just a flat chalkboard, and then you have an equation, X squared plus Y squared equals 1, and the points that obey that form a circle. So there's a map from equations of the right sort into spaces, in this case, the space being the circle. If we were in 3 dimensions, we could have X squared plus Y squared plus Z squared equals 1. That would be a sphere. Now, there are much more complicated equations, and you can have whole sets of equations, and that's a way of describing spaces. That's a subject known as algebraic geometry. You describe spaces using algebra. And Calabi-Yau spaces, among all the possible, it's just a whole zoo of things you might try to describe. But I think it's fair to say that already in the 50s, Calabi realized that there might be and he made a conjecture, the Calabi conjecture, that there might be a space with some very special properties that you could get a nice solution of. And this is an example, of course, of interaction between mathematics and physics, that you might, there was a very special kind of complicated, knotty, tied up space that you might actually be able to solve Einstein equation on that space. And these spaces had a lot of beautiful mathematical properties. And it's fair to say that it was definitely one of the prime topics in mathematics in the 20th century, understanding the spaces. And he made this conjecture, which Yau proved in the early 70s. And then we discovered that the conditions which led the mathematicians to discover, mathematicians just like things that are beautiful. That's their only criterion. They don't worry about experiment. And they don't worry about describing nature. So amazingly and very gratifyingly, we found some consistency conditions from string theory that, after rewriting them and massaging them and putting them into the language of the mathematician, turned out to be exactly the conditions that Calabi had arrived on from a completely different point of view. And whose solutions to which had been proven by Yau. So you kind of know you're on the right track, or you feel that you're on the right track. It's like a signpost that you're on the right track when your work leads you somewhere to some territory that somebody else has been driven to from some other possibly completely different point of view. And that happened many times with string theory. This was one example of it. And it happened a little bit later with Hawking's work. Things came together and, but as far as visualizing what the spaces actually are, it's pretty hard to do. There is Yau's hometown. I wanted to go with them to see it. I didn't quite make it. I might. Sometime I'll go see it. But Yau's hometown, he's a very, very famous. He's famous in the whole world, but he's very, very, very famous in China. And his hometown in Shenzhen, I think, has a statue 4 meters high of a Calabi-Yau space, of an artist's rendition of Calabi-Yau space. So that's kind of the best that you could do. But I don't I don't know what to do. They're complicated space with a lot of knobs and handles and different ways to get from A to Z, and different minimal surfaces, and a lot of beautiful a lot of very, very intricate structural properties, and yeah.
Well, maybe one way of making the Calabi-Yau spaces more tangible for us, even if we can't visualize them, is explaining their relationship to the particles in the standard model, and particularly they have a very neat relationship, as I understand it, to the three families of particles, the quarks, leptons, and bosons, that I think you played a role in discovering.
Right. Yeah, absolutely. So, okay, so you have to ask. I told you before that I talked about how the strings take on various disguises depending on exactly how they're vibrating, and or vibrating, rotating, whatever they're doing. And in that discussion, strings, before you start compactifying on Calabi-Yau spaces, that discussion was really about just 10-dimensional flat space. No compactification. But now when you have a string on a Calabi-Yau space, there are a lot more things it can do. It can spread itself out. The string can kind of spread itself out and get in some kind of resonant cyclic orbit, where it have you seen those? I've never used this analogy before, but in airports now, there's some artist, I don't know his name, but they have these things where a ball starts at the top. These sculptures, you see them at airports and stuff. They're usually like, 20 feet by 10 feet. A ball start at the top, roll down a coaster. It may go around like this and hit a lever, bounce, and wind its way around down. Have you seen those things?
Like it's a Rube Goldberg type machine?
Like a Rube Goldberg type machine, yeah.
I haven't seen these.
You haven't seen these. Maybe they're out of fashion now. But there are many ways that things can move around, bounce off, different trajectories that they could have. Like imagine a string on a Calabi-Yau space. It can bounce off one corner and go to the third corner, twirl around a couple times, come back down, go to the fourth corner, and then if everything's arranged just right, it can have some special pattern that it'll just resonate and keep repeating. So the strings can do very interesting things when they're wandering around in a Calabi-Yau space. And they're related. The interesting things that they can do are related to the topology of the Calabi-Yau space. And topology we can think of as sort of the simplest example of a topology is like, a sphere. There's no handles on a sphere, but a surface of a donut, it's like one handle. Then you can have a two-hole donut, so on. So you can have different topological surfaces. And so Calabi-Yau spaces have a lot of intricate, interrelated topology, which provides for strings resonating in a very coherent and cohesive way with the internal Calabi-Yau space. And all of this gets translated into structures that the mathematicians have spent the last century or two working out. It's very intricate. The fat textbooks on how this stuff works out. So we were able to take all that math and from it deduce the way that particles, the spectrum of particles, we needed that to understand whether string theory on a Calabi-Yau space had electrons and quarks and the right numbers of them and so on. And even more beautifully, the next question we wanted to ask is, okay, now from it would be a gross oversimplification to say that the number of species of quarks, numbers of flavors of quarks, is the number of knobs on the Calabi-Yau space. But it's some very complex version of that. Now, then the next question you want to ask is, well, how do these things bounce off each other? How do they interact? As a physicist would say, what is the coupling between the electron and the photon, or between the quark and the electron and the neutrino, or whatever? Now, this turns out, in the framework of string theory, quite beautifully, to be translated into another math question that the mathematicians had solved after a century or so of work. It wasn't a matter of just adding and subtracting. This has happened time and time again, now we come to expect it, that every time there's some question in string theory, mathematicians have already solved it, except that every once in a while, we come on a question that the mathematicians haven't solved. Then we go and talk to them and we say, hey, why haven't you guys solved this? And string theory suggests that the answer should be this. And then they'll go and they'll say, wow, that was a great question. Why didn't we think to ask that? And then they calculate for a while. And then every time this has happened, there's been agreement. And it's been stimulating both for the mathematicians and for the physicists. But string theory has had a huge impact on modern mathematics. Yeah.
Well, here is pretty much my last question that I have. And I mean, it's just come to me as you've been talking, but you said that mathematicians just like things that are beautiful. And you've just been talking a lot about math and geometry. And by this point, it should be clear to our non-string theoretician audiences, I'll put it that way, that there's a serious, non-trivial connection between string theory and mathematics. So Ed Witten, for example, won the Fields Medal, which is the equivalent of the Nobel for mathematics. And beauty in mathematics, I think, has a serious epistemic component. We were talking a bit, Leibniz came up earlier. And one of the reasons, so Leibniz and Newton independently came up with the calculus. One version, let's say Leibniz wanted to preserve infinitesimals, partially, even though he didn't believe they existed, but because they were beautiful and simplified the apparatus in many ways. And if we look at a more modern example, David Hilbert was a finitist, but he famously said, we will not be expelled from Cantor's paradise because of the immense beauty and applicability of the vast realm of infinity that Cantor brought to mathematics. And all of this just makes me wonder, since you're, as I put it, sort of an instrumentalist about string theory, or you use it as a tool to solve these problems, where aesthetics and your sense of mathematical or physical beauty, whether this plays a serious role for you in your work and the sorts of problems you pay attention to, or how you solve problems, or your intuitions about how problems will be solved.
Yeah, well, as I said, we don't have a roadmap of how to, find all the laws of nature, but we get signposts, and of course, those signposts can be interpreted in different ways. But when a problem that's trying to solve a problem in physics, and when you run into some beautiful mathematics along the way, or it leads you to some beautiful mathematics, or even better, it allows you to solve a problem. It gives you an insight that allows you to solve a problem in mathematics. You feel it's a signpost. It's some indication that you might be on the right track. So yeah, when I run into some beautiful mathematics in my work, I feel encouraged. And of course, I also love beautiful mathematics, but it's all right. But yeah.
Well, Andy, this has been absolutely terrific. It was really a wonderful way to introduce string theory and some of its applications to the show, and also to talk about some of its background and history. So I'm really so thankful for your time and expertise. Thanks for doing this with me.
Well, thank you. Thank you.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.